Hello, this is Greg Risteman from Olympus. I'd like to welcome everyone today to this webinar titled Improved Method for the Inspection of Carbon Steel Welds using Eddy Current and the NORTEC 600. This webinar is an introduction and an overview to the carbon steel weld inspection solution in oil and gas and power generation applications using the NORTEC 600 Eddy Current flaw detector. Our presenter today is Tommy Bourgeois. Tommy is the product manager for Olympus's eddy current testing and bond testing line of products. He's worked for Olympus for nearly 15 years. This informational webinar will last approximately 1 hour. If you have questions, please type them into the Q&A panel in the lower right portion of the screen during the course of the presentation. We do not monitor the chat panel for questions. If we're not able to get to your questions during the live webinar, they will be addressed personally either by email or phone after the event. Now, without further ado, I'd like to turn the presentation over to Tommy Bourgeois. Tommy, take it away.
All right, thank you very much, Greg. Welcome everybody to this afternoon session of the webinar. Thank you for your time in attending this. So without further ado, let's start with the agenda. Today, we will spend approximately 1 hour together on this webinar. We will go through a brief introduction, the challenges of the magnetic particle inspection. We'll talk about the benefits of an eddy current solution, the NORTEC 600 weld inspection solution. We're going to see some detailed features that make that an improved solution for weld inspection, and end this presentation with a live demonstration where you can see the actual instrument screen. So, what is this webinar about? Well, this is an improved carbon steel weld inspection by Olympus, and it's based on the new NORTEC 600 eddy current flaw detector. So, the industries covered are oil and gas, power generation, shipbuilding, public transportation, amusement parks, construction welding, etc. And the application is fairly simple and defined. It's the inspection of carbon steel welds in order to detect and characterize surface breaking flaws. So, where does that apply exactly? Pipelines have welds, refinery structures have numerous components and machines that have welds and are made of carbon steel, including pressure vessels, valves, flanges, and of course the offshore structures, whether it's top of water or underwater. So yes, we do have underwater probes for weld inspection. And the list goes on. We also have construction welding applications, bridges. Again, those public structures include amusement parks. You could have modern art as well, power generation structures, ships, whether it's commercial or military, and, of course, other critical welds, such as cranes. It's probably fair to say that most of the carbon steel welds are being inspected with the so-called magnetic particle inspection technology. So I'll refer to the magnetic particle as MPI throughout this webinar. Magnetic MPI uses magnetic field to magnetize the metal, and the magnetic particles can actually reveal the cracks as they align from the magnetic field disturbances. It's a fairly simple to use technology, and it can be applied on several part types. However, this is also coming with a pretty long list of challenges or problems associated with the use of that technology. Well, first, the MPI method requires to remove the paint and prepare the surface to the bare metal in order to perform the inspection. So this will not work if the paint is on. In order to remove that paint, we also need to employ strong chemical products, and not only that, additional chemical products need to be employed when the paint gets reapplied onto the surface. So, as a global trend is to employ less chemicals, more environmentally friendly processes, that definitely raises a concern across the industries. Liability. Removing the protective paint or coating eventually exposes the bare metal to the elements. So corrosion rate is accelerated, and in some cases there can be contamination of process fluids or lubricants, basically due to the chemicals being employed by the MPI technology. So the liability can be compromised by performing the inspection itself. Turnaround time and productivity is definitely another problem. As a whole, the surface preparation, the pre-cleaning, the paint scraping, the actual inspection, the post-cleaning, the reapplication of the coating, all that involves several steps and also several people, because those steps are rarely performed by the same person. That requires preparation, execution time, and basically there's a lot of time involved from preparation to putting back the part into service. When considering the entire MPI process, it takes quite a lot of time. The actual inspection itself is probably a minor part of this entire process. Of course, in all industries, time means money, especially when a critical part needs to be put back in service. So, associated with the MPI inspection, there is a hidden cost, the cost of downtime, the cost of removing the paint, the cost of reapplication of the coating, and all of that is often overlooked, but it's actually far more significant than the actual inspection cost. And that's not it. The MPI is not particularly easy to employ on those rope access applications. Scaffolding needs to be employed. And MPI is also very tough to perform when the weather conditions are not good enough. Perhaps the last issue here is that the sizing and archiving are very tough to obtain with MPI. The sizing is impossible. The archiving is certainly not easy, and it takes quite a skilled photographer and equipment in order to take a picture just like the picture below. The reporting and archiving are quite tedious. Most of the time, the results will be a simple pass or fail, and without any easy way to trace the results. So, with all that list of problems, it would be nice to have a solution that solves everything, and it happens to be eddy current. Eddy current technology solves all the problems at once because of the simple fact it does allow detection of defects through paint. Therefore, the paint does not need to be improved, and that's probably the main argument to employ eddy current, and basically that favorizes or helps spreading the eddy current across the industry as a replacement to MPI. So, Olympus just released last year a new eddy current flaw detector called the NORTEC 600. Basically, that's the instrument we're proposing to do this improved weld inspection method. It's pretty much the only instrument on the market that bears the ISO 15548 standard, or EN 15548. It's definitely a very tough, very rugged and field-ready package. We've been using that casing on a couple other instruments. It has an outstanding color display, very defined, very bright. It's, without questioning, a very intuitive instrument, and we're going to learn about application precepts. And it also offers complete archiving and reporting solution. So, in a nutshell, the benefits of the NORTEC 600 carbon steel weld inspection solution. It allows to inspect through paint or coatings up to 2 millimeters thick, and that honestly is a conservative value because it can be stretched a little bit more. It's an environmentally friendly solution because there are no chemicals involved. It also allows to size or evaluate the depth and length of indications. Well, it's definitely a solution that offers data reporting and archiving. And last but not the least, this is a rope access ready format. Now, some additional propaganda for you. The key features of the NORTEC 600 when applied to weld inspection. I don't want to list everything that's in the brochure already, but basically an almost totally sealed instrument. The only thing that's not sealed is the knob, really. So if you would immerse it in water up to the knob level, it would still work, but I would not advise to do it for the entire instrument. So it can definitely withstand some rain. I said it's EN 15548 compliant, or ISO, it's the same. It's a pretty lightweight instrument. It lasts up to 10 hours and actually almost 11. It's got a very bright, large 5.7-inch VGA display. It has a very intuitive interface with application presets. We're going to see that a little bit later. And a new gadget called real-time readings. As much as a gadget it is, it comes very handy for doing analysis of indications. Also has a storage capacity of up to 500 files. So this first section is the first of the detailed explanation as far as why this is an improved solution for carbon steel weld inspection. Detection through paint. Basically, eddy current technology uses magnetic field to couple the probe to the part being tested. The magnetic field can travel in air or through coatings such as paint. There's no difference for the magnetic field whether it's paint or air. The eddy current will work as long as the metal, basically the material being tested, is conductive. If the coating is non-conductive, it helps. It's just easier, like paint. But if it is conductive, it's not impossible. It's just a little bit tougher and might require a little bit more tweaking of the instrument, but it is also possible to do. Now, the distance from the probe to the part is called the liftoff. You will hear me speaking about liftoff quite a bit during this presentation. It's one of the key variables in this solution. And basically, the distance from the probe to the part would typically need remain minimal. And what prevents the probe from being as close as possible to the part under test is only the paint thickness. So the paint thickness will be as pretty much the equivalent of the liftoff here in this application. Liftoff of up to 2 millimeters are possible, and a little bit more. So, in order to perform weld inspection, we need special purpose coils or probes. Basically, those probes feature dual coil engineered to cancel liftoff variations. It's an ideal configuration for carbon steel, and it provides easy signal interpretation. And of course, Olympus offers quite a bit of variety in the probes, whether the probe bodies, styles, and kits are also available. So, what is the effect of the paint thickness or the liftoff? Basically, it's attenuation. So added paint or liftoff will cause attenuation on the signals. As an example, this is a calibration standard notch. It's a long notch, it's 1 millimeter deep, and we calibrate it typically at 90 degrees, 6 divisions high in the impedance plane. So that's without any paint. Okay, that gives a 80% full screen height. If we add paint, now this is exactly the same defect being scanned with added liftoff or paint thickness, and with only half a millimeter of added paint, the signal drops to 2.6 divisions. It was 6 before. Without paint, it drops to 2.6. And as we increase the paint thickness, it's going to drop further. This is 1 millimeter, provides 2.4 divisions. 1.5 millimeters paint is 1.6 divisions, and 1 division only for 2 millimeter of paint, or 1.3. So, as we plot this attenuation of the vertical amplitude in divisions against the paint thickness, we obtain an exponential decrease, which is following what the eddy current theory predicts anyway. That's not a real surprise. So what do we do? It's possible to compensate for that paint thickness in order to have a uniform sensitivity for the test as we need to have in order to have proper detection. So it's possible to recalibrate using the proper paint or shim thickness. So we use the shims in order to recalibrate and simulate paint. So all we do is increase gain in order to obtain identical results. So this is an example of a the 1 millimeter notch being inspected with 1 millimeter paint. And remember, it was 2.4 divisions before, and now that we compensated with 9.7 dB, we get back to the original 6 divisions we wanted to have. And that works with increased paint thickness. This is 2 millimeters paint, compensated with some more gain, but still, there's no drastic effect apart perhaps only a slight change in the phase of the signal due to the different operating point along the liftoff curve, but that's about it. The sensitivity is preserved as long as we compensate with the proper gain. So, speaking of the paint thickness, Olympus also offers a separated probe dedicated to measure the paint thickness. It's using the same connector as the weld probe and will monitor the paint thickness on the actual part. So why would you want to do that? Well, knowing the actual paint thickness allows to identify which shim to use over the calibration notches in order to calibrate using the proper shim assembly and compensate the gain accordingly. So if you have 1 millimeter paint on the actual part that you find using that probe, after what you should do is really use the 1 millimeter shims and recalibrate your weld inspection main probe in order to ensure that you have the proper sensitivity. So back to the paint thickness effect. That was a quick excursion just to demonstrate or talk about the paint probe. Now we're back on the main topic of the actual effect of the paint thickness or the attenuation. This is an actual example with a multi-pass, almost 30 mm wide weld inspection, sample. And this is a toe crack, 6 millimeters long, 1 millimeter deep, basically with very little paint, almost less than 0.25 mm or 7,000. And after we scan it with added paint or added liftoff and compensate for this extra paint thickness, basically the idea is that before compensation with very minimum paint thickness and after compensation, if we use the appropriate gain, we can have the same sensitivity. There's no noticeable change in the amplitude of the signal as long as we compensate for the proper paint thickness. So another example, heat affected zone crack, same dimensions, and again, without and with the paint, there's the same amplitude that is found. So there's no significant change in the signal response. And well, you might say, yeah, the signal doesn't look the same. That has more to do with the scanning than anything. But what's important is the number of vertical divisions that the signal goes. So the paint removal is definitely gone with eddy trend. No paint removal is needed. The surface, we can't say that it doesn't need to be prepared. It's minimal surface preparation because you need to make sure the probe can pass. If there would be some major deposits or something that prevents the probe to pass, you would need to remove it. But it's nothing like paint scraping or all that tedious process. Because of that, the downtime is minimal, and we also have high temperature probes to inspect the parts while they're still in service. There's no liability issues associated with the paint removal anymore. So, brings me to the section 2, defect depth evaluation. Now, this is another thing that eddy trend can do and magnetic particle cannot. Basically, that's possible because the eddy trend theory predicts that on ferromagnetic material, the amplitude will be a direct function of the flaw depth. for surface breaking, of course. So it's all relative to a calibration standard, so that's very important to have one. Eddy current cannot work without a standard. And typically the calibration would be performed on different depth notches, 0.5 mm, 1 and 2 millimeters deep EDM notches. The depth evaluation is basically a comparison of the indication amplitude against the calibration. Now this is the key sentence here. This is a relative technology to your calibration results. Basically, when you find an indication, you're always going to compare it against the calibration to estimate or evaluate the depth. And that's why we say it's a depth evaluation. It's not sizing, because sizing refers to something very precise and evaluation is an estimate. So, how to evaluate the depth of an indication? In very short, the NORTEC 600 features a new function called the instant reference signal. When you press that, you can basically save your background reference overlay. And I will demonstrate that later on during the live demo. Also, the new gadget, the real-time readings, that comes very handy because it displays, actually, it's the vertical peak-to-peak. Now, VPP means vertical peak-to-peak amplitude. It's in divisions. The units here are divisions from the null point. So right now, this indication is 5.9 divisions from here to here on the vertical axis. And that real-time reading is, of course, displaying values in real time. So, a typical calibration for depth would be performed on long notches on the standard. Basically, the process involves to record the calibration amplitudes. Either you save them in background or you note them aside the instrument. And then, so yeah, if you would save them in background, you would use the instant reference signal. And once you have those, it's important to keep them in mind as you inspect or use the background overlay. Basically here on this calibration, a 0.5 millimeters deep will provide 2 divisions. A 1 millimeter deep, 3 divisions, and a 2 millimeter would give 4 divisions. So for the next slides about depth evaluation, please keep in mind that we have 2, 3, and 4 divisions for depth of 0.5, 1, and 2 millimeters deep. Here's an example. This is not a real crack. It's an EDM located at the crevice. It's 3 millimeters deep, it's axial, and it's long of 18 millimeters. Basically, the calibration defect for the deeper flaw we had was 2 millimeters, and 2 millimeters was 4 divisions. Now, this defect clearly exceeds 4 divisions. It's 5.3 if we trust the reading here. And we know the actual is 3 mm. So basically, 2 mm is 4 divisions. We know 3 millimeters would be higher, probably between 5 and 6 divisions. So that still works. And all we can be sure here, we can't tell if it's 3 millimeters deep, but we know that's for sure that this is deeper than the 2 millimeter mark that we set during calibration. Another example, well, same dimensions of defect, just located elsewhere. It's basically a base metal crack, transverse, and we're basically, again, the calibration refers to 4 divisions for 2 millimeters deep. This actual defect is 5.2 divisions high. So again, this is deeper than 2 millimeters. And here there's a typo. The sign should be reverted. So the depth evaluation is possible, and we can tell it's deeper than 2 mm. All right, let's move to another example. Short flaws. Let's go with an actual crack that is 1 millimeter deep. The length is 5 millimeters. So for a 1 millimeter deep, according to our calibration previously, we should expect 3 divisions. Well, there's a problem because the actual defect provides 1.8 divisions only. according to this reading here. What's happening? So we have what we refer to undersizing. We have only 1.8 divisions instead of having 3 as expected. So let's see why we have that. Before that, another example. Pretty similar dimensions. Now it's an EDM located at the toe of the crack, actually. 6 millimeter, 1 millimeter deep. And again, for a 1 millimeter deep, we would expect 3 divisions, but we have only 1.9 divisions. So, and here the paint was compensated properly, so that's not a paint issue. Something else is going on. Actually, what happens is the calibration that we did earlier was adjusted on long defects. Now we have short defects, and shorter defects in the order of the length of the probe size will actually provide less amplitude and be undersized. So that comes as a limitation to the depth, to a precise depth evaluation by this method. However, as needed, this could be compensated. So if a typical weld or a given weld is known to have a lot of short flaws and somebody wishes to improve sizing on short flaws, it's possible to do it. It's possible as long as we employ new calibration set of defects. Basically, if we calibrate on short defects, on EDMs, 5 millimeters long, for instance, with different depth, it's possible to obtain a much more accurate sizing out of a better calibration. So as example here, 0.5 millimeters is typically set at 2 divisions. So a 1 millimeter would be 3 divisions. That's exactly what we have here. It's a 1 millimeter flaw. It's 3.1 divisions after we compensate by calibrating on short defects. So the bottom line or the message here is that if you would wish to improve the sizing of the defects, whether they're long or short, the NORTEC 600 allows it. It's possible to do it. Probably most of applications or users will not bother and consider the rough evaluation acceptable, but again, this is possible to refine this sizing and obtain better results for depth evaluation. Now, an additional tool, we talked briefly or occasionally about the peak-to-peak measurement. And I told I would explain a little bit later. So that's the explanation for the real-time readings, really. So different areas of the weld will have various operating points. A crevice crack would operate from here. A toe crack would operate near the null. A crest would not be far away from the null. And the base metal, depending on the actual part or weld configuration, could operate lower or higher, but also at a different null point. What happens is if an indication is found, trying to estimate its size or its vertical deflection and division is trickier because one should consider the difference from the top to the bottom of the indication. Like this indication here is more like 2 or 3 divisions high, considering the null point being lower. So the delta is important. So that's why the vertical peak-to-peak measurement tool is ideal for instant measurement to associate that with the depth, because that's providing instantaneous measurement or delta from the top to the bottom of the defect signal. So with some more examples, a crevice crack here, we can tell it's actually 3.1 divisions if we count with a simple graphic method, and the reading comes accurate at 3.1. And again, this is away from the null, and the VPP still works. Another example, the toe crack pretty much centered at the null, 2.4 divisions. 2 more examples, the base metal crack, well, that's offset by 2 divisions and extends up to the 4th division, but the length is 2 point something, and the VPP is accurate, again, says 2.6. And last example, 2 vertical divisions They're not volts. I'm used to volts from other products, but this is really about vertical divisions. The advantage of this vertical peak-to-peak reading, or basically real-time reading, is that it will provide accurate results independently from the weld zone or where the defect is on the weld. That brings me to the next section, the defect length evaluation. The length of the indication is possible to be determined with eddy current NORTEC 600 method. Basically, using the -6 dB method, the same method that's employed in ultrasonic inspections, actually for weld inspection. The ultrasonic method for weld does employ a -6 dB method. When we apply that to eddy current, we find that it's possible to have a pretty accurate length sizing. So, how to do it with the NORTEC 600? First of all, just like with ultrasonic weld inspection, find the extent of the indication. Basically, make sure to understand where it starts approximately and where it stops on the part. Then, you raise the screen, scan the entire indication, and note the total deflection of the VPP. Or an alternate way would be to press and hold that save ref key, that new function of the NORTEC 600, in order to dump the signal in background, and that's called the instant reference signal. All right, now we have basically the maximum signal from that crack indication. Let's do the next step. Slowly scan into the defect start until, basically, when paying attention to the background signal, until you reach half of it. Now, you can trust either your eyes and use the background reference signal in order to spot the middle point, or use the reading. Either or are possible and will give equivalent results. Once you found the point where the signal is actually half of the maximum, and that's the -6 dB, basically put a mark with a pencil or something alike on the actual part. Now the next step would be to keep scanning until the signal goes maximum, and when it starts to decrease again, you need to do the same exercise. So you need to spot the area where the actual signal is half of the maximum, whether you're trusting the actual reference signal or the reading. Once you found that, mark it on the part and employ a simple ruler to measure the distance between the two marks. Now, the uncertainty of that method is more associated to the ruler, but probably more the inspector or the user itself or himself, because, well, we know that the ruler couldn't be applied at different angles, and the actual parallax might make that a little bit less accurate. So it's basically a plus or minus 2 millimeters uncertainty, mostly coming from the marking and measuring method than the eddy current itself. So this is a swift example of a few defects or various lengths being plotted against basically the measured eddy current, the measured length from employing this eddy current method, as opposed to the actual length. And we can see that it all falls between the ±2 millimeters accuracy, which is not bad for a fairly simple evaluation. So another section here, complete archiving and reporting solution. The NORTEC 600 allows to save files instantly at the touch of a key. Up to 500 files, and the programs and data files get merged into a single file. So there's no more confusion between stuff like, hey, I saved my data files and I can't find them because somebody saved the program, or the opposite. I thought I saved the data, but I can't find it, and this person saved the setup. So that's not happening anymore because we basically merged that structure into a single file structure, so both the program and data are part of a single file. The NORTEC 600 also features an onboard file preview, which is this example here. That's coming from the memory of the instrument. So you can recall, set reference, hide the readings, and do various simple operations. The complete workflow of saving, archiving, reporting is actually very easy with that NORTEC 600 instrument. First of all, you need to save everything you want to save from the instrument. Once you're done inspecting, it's time to import all the files in NORTEC PC, and that can be done by 2 or 3 clicks because there's a new file import wizard into the software. Once that's done, that's all imported, you can click a single step or single click button inside the software that will export all files as PDF, and you export them on your network, on your computer, or onto a CD, and then that accounts for your archiving part and reporting at the same time. So with very minimal handling and very few steps, you can do the entire workflow very easily. So last session before the demonstration, rope access ready. The NORTEC 600 is definitely rope access ready because it weighs only 1.6, 1.7 kilos or 3.7 pounds. It's got an ergonomic design with the factory installed hand strap. It has 4-point anchors to attach a chest harness, and we actually sell one as an optional accessory. It's a very tough, very rugged design that can endure some beating. It's got an excellent stand or handle, so you can actually freely fold that stand. We call that the pipe stand. So it's got high friction. You can put it on the curved surface, or you can basically stretch the stand to use it as a hook. This is designed for IP66. Again, will endure a very severe rain, and it has over 10 hours of battery life. Now, the screen is something on this instrument. It's got the NORTEC 600 has an excellent screen legibility and brightness, perhaps one of the best, if not the best, in the industry. It has also a true full screen mode that's accessible from a key here. It's called full screen. So going full screen to menu screen is easy. And the interface is actually extremely easy, and in a few minutes I will demonstrate that with my display of the instrument screen. So we have those application presets. That's basically covering for the most common eddy current applications in the industry. And those are factory presets that will preset pretty much everything in order to have the user do minimal or less operations and get results faster. So all those parameters were adjusted based on customer feedback, based on our own experience with the different applications. And everybody that started to use that really liked it. And of course, if you don't like it, you can always turn that window off. It's possible to turn it off in the instrument. So another gadget that comes with the NORTEC 600, it's called the calibration from frozen signals. So imagine you just scanned your notch once. Now you can set the probe aside so it frees up your hands, and you can freeze the instrument and adjust your gain pretty much without having to rescan the part. Now this comes very handy, especially if you're hanging from a rope, on rope access of course, and need to calibrate or reconfirm calibration. So obviously Olympus offers a wide variety of probes, standard probes, high temperature, high wear, underwater, those are underwater series, special designs, bigger, different ergonomics, and there's a bunch of custom probes I haven't shown there, but we have an extensive selection of weld probes adapted to many situations. So it looks like it's time for a live demonstration. So I will share actually a I will change the display here to share the display of the NORTEC 600 I have. So how that works, basically I have a small VGA capture device that's plugged into my presenting computer, and I'm basically showing you the VGA output of the NORTEC 600. Well, the only thing that's missing here is you basically don't see what I do, so I will have to explain everything that I'm doing, and of course you don't see the keys of the instrument or the knob, so I will explain some of it as well. Now this is a demonstration to demonstrate how easy the NORTEC 600 is to perform a weld inspection, but it's also an intent to demonstrate the key features for that solution. So, first of all, the application selection. Basically, now I'm rotating the knob of the instrument just to show you that that can be updated. The application selection, again, those are presets that will preset pretty much everything for various applications. Now I have weld inspection, so I will select it. And basically, once I exit this menu, it's ready to work. So I just hit the main key, and I find that my frequency is already pre-adjusted. All right. The 100 kilohertz is the industry standard. It's defined in the EN 1711 standard. So let's go and do a calibration. So I'm going to, right now I'm putting the probe on the standard, and I'm scanning the 1 millimeter notch. And here's the calibration and freeze feature. So watch what I'm doing here. I'm actually freezing the instrument, okay? And I'm putting the probe aside. So right now I don't hold the probe in my hands. I put my two hands or one single hand on the instrument. I can do that from a single hand. As I'm talking, that's exactly what I'm doing. So I press the angle key, and remember that the signal is frozen right now. So I'm actually doing my calibration without having to rescan that standard. So now I'm adjusting the gain in order to reach 6 divisions higher. Okay, now that I'm done, I will unfreeze this signal, and I will just rescan that 1 millimeter deep notch. And we saw it was 6.1 divisions, so let's reduce the gain just a little bit, make sure I'm fine, 6.0, okay? So I'm repeatedly erasing the screen, as you can see. So that's the 1 millimeter notch, and the real-time reading says it's 6.0 divisions. So that comes quite handy to actually display the amplitude that can be associated to depth. So if I scan a 0.5 millimeter defect, I get 4.1 divisions. Now, I talked to you about a full screen mode. Let's go full screen. So again, now I'm going to scan the 0.5 millimeter notch and the 1 millimeter, and now I will display the instant reference signal. So what I'm doing, I'm keeping the probe still. I press and hold the reference signal, and I don't know if you heard it in the microphone, but the instrument emitted a beep to acknowledge that it's got the reference signal. And now as I read the screen, all that nice reference signal gets dumped in the background. So it's now very easy to remember your calibration references, because now we can see the defects we calibrated on for depth evaluation. And of course, if I go normal screen, that reference signal gets preserved, okay? So now it's possible to do this depth evaluation. So a last feature I want to talk to you about, and that was announced in the webinar. You might have seen an alternate configuration. Well, let's see that. Basically, now I switched to an actual weld sample that has a couple notches on it. So I'm scanning a notch at the toe of a notch at the toe of the weld, and now I'm moving the probe over the weld crest. So that transition you just saw is actually the weld signal, the weld itself without any defect. And as I scan over it, there's another crack. Okay? So, well, somebody can do easily inspection with that because we can always erase the screen and use the maximum, the vertical P2P indication here, 2.7 or something, to size the indication or to evaluate the depth. But it's also possible to do an alternate configuration and basically recalibrate this in order to reduce that annoying effect of having a strong weld signal. So let's rescan that. So again, I'm just going to rescan that toe crack, now the weld crest, and I will do the same trick as before. I will freeze my screen. Now I will use the angle and lower basically that weld signal. I will just put that horizontal. Now I will press gain until I have the horizontal gain, and I will reduce the horizontal gain in order to have not more than 2 divisions wide. As I press again to have the vertical gain, oops, I will adjust my angle a little bit. Okay. Yep. So as I increase my vertical gain, I basically made sure that I retrieve my sensitivity of the earlier test. So now I can unfreeze that screen, and basically I should have a much easier signal to interpret because I don't have to worry about the weld signal since it has been put horizontal. And that is actually very interesting because if I do an alternate displays, I can actually switch to sweep and then basically sweep and impedance, where I can show the cracks a lot more easy by doing this. So because the weld signal is mostly horizontal, we don't get to see it from the vertical strip chart. So if you would need to display a strip chart, it's possible to do in this instrument. You could actually display only a strip chart. It's called a sweep. Okay, so as you scan across notches, you would have basically a history of this eddy current signal. Okay, so that quite concludes my live demonstration. So I will return to the main PowerPoint presentation here just to give you a couple more slides for the conclusion. So as a wrap-up, the NORTEC 600 weld inspection solution versus the magnetic particle. Well, as we just saw, both are fairly easy to use. The new NORTEC 600 is definitely a much easier to use instrument than anything else by the past competitor equipment or Olympus equipment. Definitely a drastic improvement in that aspect. So then the list of problems of the MPI basically are becoming solutions with the NORTEC side. So the NORTEC 600 weld inspection solution can inspect through paint, and of course the MPI requires removing of the paint. So sizing or depth evaluation is possible and not with MPI. Liability issues that are tied to removal of the paint are not found with eddy current or NORTEC 600 solution. It's a very fast inspection with very minimal preparation, and the MPI involves long turnaround time and also longer inspection. So archiving and reporting are possible to do, and that's actually very easy to do on the NORTEC 600, and MPI doesn't allow easy archiving. The NORTEC is definitely suited for rope access, and it's also environmentally friendly. No need for any chemicals with that solution. So, as a conclusion, the NORTEC 600 weld inspection solution is ideal replacement to the MPI method. There's no need to remove the paint. It's environmentally friendly, no chemicals. It can evaluate the depth and length of indications. It's possible to do data reporting and archiving, and it's definitely a rope access package. So, if you have questions, we can use 1 or 2 minutes to answer questions of general interest Otherwise, we will also review all the questions offline within a couple days after this webinar, and we will answer them by private emails to each one of you. And so again, I'm just checking the question. I see one here. Well, for the sake of keeping this webinar short for everybody, I will answer that offline. That could be a lengthy answer. So again, thank you everybody for your attendance today. Don't forget to visit the Olympus-IMS website for a lot of information on all of our products, including the NORTEC 600 and the NORTEC 600 weld inspection solution. There's going to be a video on the weld inspection very soon, maybe tomorrow or something. We're going to put online a video on that solution. There's also product brochures and other video on the instrument and product manuals, step-by-step guides, a lot of materials available from the website. So again, thank you everybody for your attendance. I hope you enjoyed that show. If you have additional questions, please send them to us. Thanks and have a good day.
Thank you, Tommy. On behalf of Olympus, I'd like to thank all the attendees for joining us today and Tommy for his expertise and participation in today's event. We hope the material presented was informative and useful. This webinar, along with the Q&A session, will be archived on our website at www.olympus-ims.com. Everyone who registered for this event will receive a follow-up email with links to the archived presentation. That's going to do it for today. Thanks again for attending, and we'll see you again next time from Olympus Webinars.